Hello everyone, welcome to the lecture again. So far we have seen how we can find out the moment of inertia about the x, y and z axis. Today we are going to learn how we can find out the moment of inertia about an arbitrary axis. For that we require the concept of product of inertia. We will also learn what is principal axis of inertia. So, moment of inertia about an arbitrary axis. Okay. Let us say I have a rigid body and let us fix some point O, then these are the x axis, y axis and the z axis. Let us take a small mass dm and let us say this mass dm, its position vector is r and of course in Cartesian coordinate its coordinates are x, y and z. Okay. Let us say I want to find out the moment of inertia of this rigid body about the axis OL. Okay. To find out the moment of inertia, let us say that the unit vector along OL is lambda cap and this lambda cap is making an angle theta with vector r and the perpendicular distance from mass dm to OL is p. Okay. Then the moment of inertia with respect to any axis, okay, here in that axis is OL and let us say its direction cosines are known because I know at what angle this axis is. So, that is given to me. So, that has direction cosine, let us say alpha, beta and gamma and this axis passes through the coordinate origin O. Okay. Now, the moment of inertia of this rigid body about OL will be integral p square dm and from the geometry this p I can write down as lambda cap cross vector r square dm. Okay. You can see it clearly because again from the geometry my p will be r sin theta and lambda cross r will also be r sin theta because lambda cap cross vector r is lambda cap r and then the angle between them. So, sin theta and this is equal to 1 because that is a unit vector. So, we again get r sin theta. So, now this lambda cap has a direction cosine of L, M and N and this is just a vector product. So, let us find out what is lambda cap cross r. So, lambda cap cross r will be I, j and k, L, M and N and vector r is x, y and z. Okay. So, this will be equal to integral mz minus yn square plus minus lz minus nx square plus yl minus mx square into dm, okay, because there is mod. So, there will be this plus sign. Now, let us expand this. So, we have integral m square z square plus y square n square minus 2 m n y z plus L square Z square plus N square X square minus 2nl zx plus y square l square plus m square x square minus 2yx lm and then dm. Okay. Now, let us collect the coefficient of L square, M square, N square and note that the L, M and N are constant. So, we can take it outside the integral because the orientation of the OL is fixed. So, therefore, L, M and N are constant. So, let me collect the coefficient of L square. I have taken it outside the integral y square plus z square dm plus m square integral z square plus x square dm plus n square integral x square plus y square dm minus 2lm integral xy dm minus 2mn integral yz dm minus 2nl integral zx dm. Let me define this quantity as Ixy equal to integral xy dm. Similarly, Iyz equal to integral yz dm and Izx as integral zx dm. Okay. So, these quantities are called the mass product of inertia or the product of inertia. Okay. So, the moment of inertia of this rigid body about OL becomes I xx L square plus I yy m square plus I zz n square. So, here Ixx is the moment of inertia of this body about the x axis. Okay. Iyy is the moment of inertia about the y axis. So, Ixx is this, okay, minus 2Ixy Lm minus 2Iyz Mn minus 2Izx Ln. Okay. Let me call this equation number A. Okay. So, what this equation tells me? This equation tells me that if I know Ixx, which is the moment of inertia of this body about the x axis, Iyy is the moment of inertia about the y axis and Izz along with Ixy, Iyz and Izx, which are the product of inertia, then I can find out the moment of inertia of this body about OL. Okay. Let me write down this statement. Let me again first write down what is IOL. So, this is the same equation that I am writing here. It is Ixx L square plus Iyy m square plus Izz n square minus 2 Ixy Lm minus 2 Iyz Mn minus 2 Izx Ln. I call this equation number A. So, this equation tells me, as I said, if the component Ixx, Iyy, Izz, Ixy, Iyz and Izx are known at a point. So, that point is O here. Then the moment of inertia about any axis through the point can be found, okay, and it can be found by equation number A. Now, this equation I can write down in the matrix form. So, I can write down as Ixx, Iyy, Izz, and then I have these 2 xy. So, let me write down minus Ixy here and minus Ixy there, and similarly I have 2 yz. So, let me write down minus Izzy minus Iyz or zy, and minus Ixz minus Ixz. Okay. So, I have just arranged them in the matrix. Now, this matrix is known as the inertia matrix or the inertia tensor. Okay. Before we discuss further, let us look at the product of inertia, and let me say that the calculation of the product of inertia is similar to the moment of inertia calculation, and also the parallel axis theorem holds here. So, let me show you the parallel axis theorem for product of inertia. So, for that let us say I have a rigid body, okay, and this is the x axis and this one is the y axis. Let us say I make another axis which passes through G, the center of mass. So, let me call it x naught and y naught. Let us take a small mass dm, and in x naught y naught coordinate system, its coordinate are x naught and y naught. Similarly, in x y coordinate system, the coordinates are x and y. Let us say this x naught and y naught are situated at a distance of dx and dy. So, this is dx and this one is dy. Now, the product of inertia I x y will be integral x y dm, and this I can write down as integral x is equal to x naught plus dx. Okay. Similarly, y equal to y naught plus dy and dm. So, this I can expand x naught y naught dm plus dx dy integral dm plus dx integral y naught dm plus dy integral x naught dm. Okay. But note that this x naught and y naught, they are measured from the center of mass, therefore, integral y naught dm will be 0, it is the first moment. Okay. So, this and this will be 0 because that is the definition of the center of mass. So, therefore, I am left with integral x naught y naught dm. So, this is nothing but the product of inertia about x naught y naught plus m into dx dy. Okay. And I x naught y naught is the product of inertia about the center of mass. So, I can rewrite this as I x y equal to I x y about the center of mass plus m dx dy. And the same thing is true for the product of inertia about x z. So, that will be I x z plus m dx dz, and similarly I y z equal to I y z plus m dy dz. Okay. So, it holds. Now, let us look at a very simple example about the product of inertia. So, the problem statement is following. a plate has uniform thickness T which is negligible compared with its other dimension. Okay. The density of the plate material is rho. Determine the products of inertia of the plate with respect to the axis h chosen. Okay. So, here we have to find out the product of inertia of this plate about the x, y and z axis. So, first of all it is given that the thickness is negligible. Okay. Since the thickness is negligible, therefore, so let me write down, since the thickness is negligible, therefore, I x z equal to I y z equal to 0, because when you calculate x z there will be integral x z dm, and since z is almost 0, so therefore, the integral will be 0, and the same thing is true for I y z. Now, let us see what is I x y. So, I x y I can find out if I know the product of inertia about the center of mass, then I can just do I x y bar plus m dx dy. So, let me put an axis at the center of mass. So, this is my y, let us say y 0, similarly x 0, and you have z 0. Now, from the symmetry, okay, I x y bar will be 0. Okay. This also we can see mathematically. So, I x y is nothing but integral x y dm, and that will be equal to, so let me take the limit minus a by 2 to plus a by 2, and for the y it is minus b by 2 to plus b by 2 x y and mass dm. Okay. So, mass will be the density times the volume. So, thickness is t, which is small, and then dx dy. Okay. So, that will be equal to rho t minus a by 2 to a by 2 minus b by 2 to b by 2 x y dx dy, which is of course 0. Let us put this in equation number 1. So, I have I x y equal to 0 plus m, mass is rho times the volume. So, t into a into b, and then dx, dx is the distance of this g from x. So, that will be dx and this will be dy. So, dx is a by 2 and dy is b by 2. So, that comes out to be 1 by 4 rho t a square b square. Okay. Now, let us come back to the discussion of the moment of inertia about an arbitrary axis. We saw that the inertia matrix I was I x x minus I x y minus I x z minus I x y, I y y minus I y z minus I x z minus I z y and I z z. Okay. Now, let me write down the definition of the principal axis of inertia. Okay. And let me remind you, the situation was following: we had this rigid body, we fix some point O, then the Cartesian axis were x, y and z, and we wanted to find out what is the moment of inertia of this body about an arbitrary axis, let us say OL. So, the statement is following: if we examine the moment and product of inertia term for all possible orientation of the axis with respect to the body for a given origin. So, that given origin is O here, then there exists an orientation of the x y z axis for which the product of inertia term vanishes. Okay. So, what you do is, we have this point O, we call this given origin. Now, you find out the moment of inertia for all the possible orientation of these x, y and z axis. So, let us say one possible orientation is this x prime, y prime, z prime. Another possible orientation may be x double prime, y double prime, z double prime and so on. Then there will always exist some orientation of the x, y, z for which the product of inertia term will not be there. Okay. So, all this term will become 0. Okay. So, that means for that particular orientation we have the inertia matrix I equal to Ixx, let me call it I1, Iyy and Izz for that new orientation, and there will not be any product of inertia term. Okay. Here this I1, I2 and I3 are called the principal moment of inertia at point O, and the corresponding coordinate axis are called the principal axis. Okay. Now, the question is, how do I find out the principal moment of inertia and the principal axis? Now, this is something that I am not proving it, but it can be shown that the solution of the determinate equation. Okay. So, I have this matrix and I have that matrix. So, let us make a determinate I x x minus I minus Ixy minus Ixz minus Iyx, Iyy minus I minus Iyz minus Izx minus Ixzy, Izz minus I equal to 0 will give you I1, I2 and I3, which are the 3 principal moment of inertia. Okay. Let me just call this equation number B. Now, the direction cosine okay, L, M and N of the principal axis are given by, so first of all this L, M and N, they will satisfy the relation, you know that L square plus M square plus N square equal to 1. Okay. Also we have Ixx minus I into L minus Ixy into M minus Ixz into N equal to 0 minus Ixyl plus Iyy minus Im minus Iyz into N equal to 0 and minus Izxl minus Izym plus Izz minus I into N equal to 0. Let me call this as equation number C. Then this equation will give a solution for the direction cosine for each of the 3 i's, that is I1, I2 and I3. So, let me just repeat again. You have a rigid body, let us say there is some point O and we have the x axis, y axis and the z axis, and of course about this x, y and z axis, this body has some product of inertias. Now, if you orient your x, y and z axis, then you will always find some x prime, y prime and z prime such that the product of inertia of this body will vanish and you will only have the moment of inertia. Okay. These moment of inertia are called the principal moment of inertia, and the direction cosines of this x prime, y prime and z prime we can find out. With this, let me stop here. See you in the next class. Thank you.